Welcome to the History of Simple Things, where we delve into the fascinating history behind the little things that shape our world. Have you ever looked up at the power lines crisscrossing the sky and wondered why they always seem to come in sets of three? High-voltage power lines are a common sight, yet their arrangement holds a fascinating story rooted in the principles of electrical engineering. Today, we're going to delve into the science and reasoning behind this ubiquitous trio of wires. High-voltage power lines are essential for transporting electricity over long distances, from power plants to our homes and businesses. The reason they typically come in sets of three is due to the use of a system called three-phase electrical power. This system is a standard method for AC electric power generation, transmission, and distribution. But what exactly is three-phase power, and why is it so important? Three-phase power is a type of polyphase system used by electrical grids worldwide. In this system, electricity is generated in three separate waves, each 120 degrees out of phase with the others. This means that at any given moment, one of the phases is peaking, while another is at its lowest point, and the third is somewhere in between. This balance creates a continuous and stable flow of power, which is crucial for both efficiency and reliability. Let's break it down a bit further. Imagine each phase as a sine wave. When one phase reaches its peak, the other two are either rising or falling. This staggered timing reduces the likelihood of power surges and dips, making the system more stable. The consistent power flow means that three-phase systems can deliver more power with less loss, which is why they're favored for high-voltage transmission. Beyond just efficiency and reliability, three-phase power systems offer several practical advantages. For instance, they are more efficient for heavy industrial equipment, which often requires large amounts of power. Factories, office buildings, and other large facilities benefit from the steady and robust power supply provided by three-phase systems. Moreover, the equipment designed to run on three-phase power is generally simpler and more efficient than that designed for single-phase power. Another reason for using three-phase power is its compatibility with transformers. These devices step up or step down voltage levels, making it possible to transmit electricity over long distances without significant loss. Three-phase transformers are more efficient and less bulky than their single-phase counterparts, which is vital for maintaining a streamlined and effective power grid. The adoption of three-phase power dates back to the late 19th and early 20th centuries during the early days of electrical engineering. Pioneers like Nikola Tesla and George Westinghouse championed AC power systems, and the three-phase configuration quickly emerged as the optimal solution for large-scale power distribution. Its ability to deliver power more efficiently over long distances revolutionized the way electricity was transmitted and laid the foundation for the modern electrical grid. The next time you see a set of three high-voltage power lines stretching across the landscape, you'll know that their arrangement is no accident. It's a testament to the ingenuity of electrical engineers and the enduring principles of three-phase power. This system ensures that we have a reliable, efficient, and powerful way to deliver electricity from its generation point to where it's needed most. But there's more to the story. The uniformity of three-phase power lines also plays a critical role in maintaining the balance of the electrical grid. Each phase carries the same amount of power, but because they are 120 degrees out of phase with each other, the total power delivered to a load is smoother and more constant than with single-phase power. This smooth delivery is particularly important for sensitive electronic equipment, which can be easily damaged by fluctuations in power supply. Furthermore, the use of three-phase power simplifies the design and operation of electrical motors and generators, which are commonly used in industrial applications. Three-phase motors, for example, have a simpler and more robust design compared to single-phase motors, which makes them more reliable and easier to maintain. The inherent advantages of three-phase power also extend to renewable energy systems, such as wind turbines and solar farms, which often generate power in three-phase configurations to maximize efficiency and compatibility with the grid. The adaptability of three-phase power systems to new and emerging technologies highlights their enduring relevance. As we innovate and develop new ways to generate and distribute electricity, the fundamental principles of three-phase power will remain a cornerstone of our electrical infrastructure. This adaptability ensures that we can continue to rely on a stable and efficient power supply, even as the sources of that power evolve. Thank you for joining us on this electrifying journey into the world of high-voltage power lines. We hope you've gained a deeper understanding of why these lines come in sets of three and how they play a crucial role in our daily lives. Today we're diving deep into a fascinating topic that often goes unnoticed but plays a crucial role in our daily lives. High-voltage ceramic insulators, specifically why they have those distinctive disc shapes. By the end of this video, you'll have a thorough understanding of the purpose and benefits of these discs in high-voltage ceramic insulators. Let's get started. First, let's start with the basics. What exactly is a ceramic insulator? Ceramic insulators are critical components in electrical systems, used to prevent the unwanted flow of current to the ground from an electrical conductor. They are crafted from high-strength porcelain, a type of ceramic known for its durability and excellent insulating properties. These insulators have been a part of our electrical infrastructure since the 1950s, replacing the older glass insulators due to their superior performance and longevity. In high-voltage applications, such as power transmission lines, insulators must withstand not only electrical stress, but also environmental factors like weather changes, pollution, and physical wear and tear. This is where the design and material of the insulator become crucial. High-voltage ceramic insulators are preferred because they offer high dielectric strength, which means they can resist electrical breakdown even under intense electrical fields. Now let's focus on the primary subject of our video, the discs on high-voltage ceramic insulators. These discs, often seen stacked in a string formation, are not just a random design choice. They serve several important functions that enhance the performance and reliability of the insulators. The primary reason for the disc design is to improve electrical insulation. Each disc acts as a barrier to electric current, preventing leakage. In high-voltage transmission, the potential difference between the conductor and the ground can be extremely high. A single solid insulator would not be practical due to the risk of electrical breakdown. By using a series of discs, the potential difference is divided among them, reducing the voltage stress on each individual unit. This configuration significantly lowers the risk of flashover, where electricity arcs across the surface of the insulator. Mechanical strength is another critical factor. Transmission lines can be subjected to various mechanical stresses, including tension from the wires, wind pressure, and even ice loading in colder climates. The disc-shaped insulators distribute these mechanical stresses evenly along the length of the insulator string. This distribution helps to prevent mechanical failure, ensuring the insulators can support the weight and tension of the wires they are holding. Environmental factors such as pollution and weather can affect the performance of insulators. Dust, salt, and industrial pollutants can settle on the surface of insulators, creating a conductive path for leakage currents. The disc design minimizes this risk in two ways. First, the shape and orientation of the discs create a larger surface area, making it harder for contaminants to form a continuous conductive path. Second, rain and wind can more effectively clean the insulator surface, maintaining its insulating properties. There are several types of high-voltage ceramic insulators, each designed for specific applications and stress conditions. Let's go through some of the common types. Pin-type insulators are mounted on a pin on the crossarm of poles. These are used for relatively lower voltage lines and consist of a single ceramic unit. Their design includes a head and a body, with the head supporting the conductor. Suspension-type insulators are the ones most commonly associated with the disc design. They are used for higher voltage applications and are suspended from towers, with the conductor hanging below. The string of discs allows for the handling of higher voltages and greater mechanical stresses. Lastly, strain insulators are used in situations where the wire has to withstand tensile stress, such as at the end of a line or at sharp turns. They are also disc-shaped and are used to handle the mechanical load from the conductor tension. Let's now talk about the advantages of using ceramic insulators. Ceramic insulators offer several advantages over other types of insulators, such as those made from polymer or glass. Their hardness and wear resistance ensure longevity and consistent performance. Ceramic materials are also highly resistant to corrosion, making them ideal for use in harsh outdoor environments. Moreover, ceramics have excellent thermal conductivity, which helps in dissipating the heat generated by electrical currents. The manufacturing process of ceramic insulators involves several stages, ensuring they meet the high standards required for high-voltage applications. The raw materials, typically a mixture of clay, quartz, and feldspar, are first shaped into the desired form. This is followed by a glazing process to enhance the surface properties, and then firing at high temperatures to achieve the necessary mechanical strength and electrical properties. Ceramic insulators are used across a wide range of applications, from power distribution to industrial machinery and even household appliances. Maintaining these insulators involves regular inspections and cleaning to ensure their surfaces remain free of contaminants that could affect their insulating properties. Advanced techniques, such as ultrasonic cleaning and high-pressure washing, are often used in power transmission lines to maintain the efficiency and reliability of the insulators. As we conclude our journey, the disc design of high-voltage ceramic insulators is a result of careful engineering to enhance their electrical insulation, mechanical strength, and ability to withstand environmental conditions. These insulators are vital for the safe and efficient operation of high-voltage power transmission systems, ensuring that electricity can be delivered over long distances without loss or hazards. The use of ceramics in these insulators offers additional benefits in terms of durability, resistance to corrosion, and thermal stability. We hope this video has provided you with a comprehensive understanding of why high-voltage ceramic insulators have discs and the critical role they play in our electrical infrastructure. Hello, everyone. Today, we're diving into the fascinating and often overlooked world of high-voltage power lines. These towering giants are critical to our modern way of life, ensuring that electricity flows from power plants to homes, businesses, and industries. But have you ever wondered what it takes to service and repair these immense structures? In this video, we'll explore the intricate processes, the skilled professionals, and the cutting-edge technology involved in maintaining the reliability of our electrical grid. So sit back, relax, and get ready to learn about the incredible work that goes into keeping the lights on. High-voltage power lines are the backbone of our electrical transmission system. They carry electricity over long distances, from generation facilities like power plants, hydroelectric dams, and wind farms, to substations where the voltage is reduced for distribution to homes and businesses. These lines are typically classified into different voltage levels: high voltage, HV, extra high voltage, EHV, and ultra high voltage, UHV. The voltage levels can range from tens of thousands to over 1,000,000 volts. The higher the voltage, the more efficient it is to transmit electricity over vast distances, reducing energy losses along the way. The structures that support these lines are equally impressive. Transmission towers, often called pylons, can reach heights of up to 200 feet or more. These towers are usually made of steel and are designed to withstand extreme weather conditions, such as high winds, ice, and lightning strikes. The cables or conductors are made of materials like aluminum and steel, chosen for their excellent conductivity and strength. Insulators, typically made of porcelain or composite materials, prevent the high-voltage electricity from grounding through the towers. Maintaining and repairing high-voltage power lines is a critical task that ensures the stability and reliability of the electrical grid. Any disruption in the transmission lines can lead to power outages, which can have far-reaching consequences for households, businesses, and essential services like hospitals and emergency response centers. Regular maintenance helps identify potential issues before they become major problems, reducing the risk of unexpected failures. The maintenance and repair of high-voltage power lines involve several key activities. These include routine inspections, cleaning, tightening of connections, replacement of damaged components, and ensuring the structural integrity of the towers. Given the high stakes and the dangerous nature of the work, it requires highly skilled and specially trained professionals. These linemen, or line workers, undergo rigorous training to safely work with high-voltage electricity and perform their tasks at great heights. Linemen are the unsung heroes of the electrical grid. Their job is both physically demanding and highly technical, requiring a deep understanding of electrical systems, safety protocols, and specialized tools and equipment. One of the most remarkable aspects of a lineman's job is their ability to work on live power lines. This technique, known as live line or hot stick work, allows repairs and maintenance to be performed without shutting down the power supply. This is crucial for minimizing disruptions and maintaining a stable electrical grid. To work on live lines, linemen use specialized tools made of insulating materials, such as fiberglass poles, to avoid direct contact with the high-voltage electricity. They also wear protective gear, including rubber gloves and sleeves, to further reduce the risk of electrical shocks. Inspection and monitoring are the first steps in maintaining high-voltage power lines. Regular inspections help identify potential issues like corrosion, damage to insulators, wear and tear on conductors, and structural problems with the towers. These inspections can be performed in several ways, including visual inspections, infrared thermography, and drone surveys. Visual inspections are often conducted by linemen who physically climb the towers to examine the components up close. This hands-on approach allows for a detailed assessment of the condition of the power lines and support structures. Infrared thermography is a non-contact method that uses infrared cameras to detect hotspots on electrical components. These hotspots can indicate problems such as loose connections or overloaded conductors, which need to be addressed before they lead to failures. In recent years, drones have become an invaluable tool for inspecting high-voltage power lines. Equipped with high-resolution cameras and other sensors, drones can quickly and safely survey large sections of the grid, capturing detailed images and data. This information can be analyzed to identify issues that might not be visible from the ground or during routine inspections. Drones also reduce the need for linemen to climb towers, minimizing the risks associated with this task. Cleaning and maintenance are essential for ensuring the longevity and reliability of high-voltage power lines. Over time, dirt, dust, bird droppings, and other contaminants can accumulate on the insulators, reducing their effectiveness and potentially causing electrical arcing. Cleaning these insulators is a delicate process that must be done with care to avoid damage. One common method for cleaning insulators is using pressurized water. This technique involves spraying the insulators with a high-pressure water jet, which removes the contaminants without the need for physical contact. In some cases, linemen may also use brushes or other tools to clean the insulators manually. It's important to note that cleaning is often done while the power lines are still energized, so safety precautions are paramount. Routine maintenance also includes tightening connections and replacing damaged or worn components. This can involve tasks such as replacing conductors that have become corroded or frayed, swapping out old insulators for new ones, and ensuring that all bolts and fasteners are secure. These maintenance activities help prevent minor issues from escalating into major problems that could lead to power outages. Despite the best efforts to maintain the power lines, emergencies can still occur. Severe weather events such as storms, hurricanes, and ice storms can cause significant damage to the electrical grid. When a power line is damaged, it is crucial to restore service as quickly as possible to minimize the impact on customers and critical infrastructure. Emergency repairs require a coordinated effort from linemen, engineers, and other utility workers. The first step is to assess the extent of the damage and develop a plan for restoration. This may involve bringing in additional crews and equipment, especially if the damage is widespread. Linemen must work quickly and efficiently to repair or replace damaged conductors, insulators, and towers. This can be challenging, especially in difficult terrain or adverse weather conditions. One of the key tools for emergency repairs is the use of helicopters. Helicopters can quickly transport linemen and equipment to remote or inaccessible areas, allowing them to perform repairs more rapidly. In some cases, linemen may even work from the helicopter itself, using specialized tools to make repairs without landing. This aerial approach can significantly speed up the restoration process and reduce downtime. The future of power line maintenance and repair looks promising, with ongoing advancements in technology and methods that will continue to improve efficiency and safety. As the demand for electricity grows and the grid becomes more complex, the role of linemen and other utility workers will remain crucial. The maintenance and repair of high-voltage power lines is a complex and critical task that ensures the stability and reliability of our electrical grid. From routine inspections and cleaning to emergency repairs and advanced technologies, the work of linemen and other utility workers is essential to keeping the lights on. As technology continues to evolve, we can expect even greater improvements in the efficiency and safety of power line maintenance, helping to meet the growing demand for electricity and support the transition to a more sustainable energy future. Thank you for watching. We hope you enjoyed this deep dive into the world of high-voltage power lines. If you found this video informative, please give it a thumbs up and subscribe to our channel for more content on the fascinating world of engineering and technology. See you next time. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.